So in the previous video, we took a look at the derivatives and integrals of these different inverse trigonometric functions. And today we're actually going to go ahead and apply that knowledge for integrating like slightly more advanced or complicated rational functions. And so as a little bit of a reminder, the derivative with respect to x of arctangent of x, which is just inverse tangent of x, is going to be equal to 1 over 1 plus x squared. And when we kind of want to use the chain rule, if we were to take the derivative of arctangent of x over a, we would just get a over a squared plus x squared, which we can rewrite as 1 over a times 1 over 1 plus x over a quantity squared. So that's a little bit of a mouthful, but that's essentially, these are just two different little identities or sort of derivatives that are very helpful to know when we're integrating these very advanced rational functions. And of course, a over here is just a real constant. And so let's go ahead and apply this knowledge to integrating these rational functions. So let's say we're taking the indefinite integral of 12 over 1 plus 9x squared dx. And so this one is slightly more advanced. We have an x squared in the denominator, but we don't have anything in the numerator, kind of do a u substitution and get natural log of x. Instead, what we're going to do here is we're going to try to get it in one of these forms, in the form of 1 over 1 plus x squared. And so essentially to do that, it could be helpful to rewrite this 9x squared over here. We know that 9 is a perfect square and that x squared is a perfect square. So 9x squared is really just equal to 3x quantity squared, right? Because you distribute that square, you get 9x squared. And so we can write this as the integral of 12 over 1 plus 3x quantity squared dx. And now we can do a little bit of a substitution. Here we have a 3x. What we really want is just an x, or in this case, we can use any variables. Let's just say a u. And so here we can say let u equal to 3x, which indicates that du by dx would be equal to 3. So du is equal to 3 dx. And so with this in mind, now we can just go ahead and start substituting. So here we have a 12 times dx. What we really want is just a 3 times dx. But we know that 12 is basically just 3 times 4, right? This is just 3 times 4, so we can go ahead and take that 4 out of the integral. This will just become the integral, or 4 times the integral of 3 over 1 plus 3x quantity squared dx. And now we can actually substitute. So we have a 3 times dx over here, that's just du. We have a 3x quantity squared, that's just going to be, well, 3x is just u, so 3x quantity squared is just going to be u squared. So this is ultimately equal to 4 times the integral of 1 over 1 plus u squared du. And now we have it in this form over here, this 1 over 1 plus something squared form. And so this is going to be equal to 4 times, here we have, instead of an x, we have a u, so this is just going to be equal to arctangent of u, and then plus c. And we want to go back into x, so we can just substitute u equals 3x, so we get 4 times arctangent of 3x plus c. And so that right over there would be our final answer. And so essentially here, the point is that we just have to use u substitution and get it in this form. It's a different sort of form than what we've seen before, but fundamentally it's just u substitution, trying to manipulate the integral a little bit to get it in this very familiar form. And so let's go ahead and apply this to a slightly more advanced example over here, where we may actually have to use u substitution twice, as you'll come to find. So we have the integral of e to the 2x over 4 plus e to the 4x. Now, something you may notice is that we have e to the 2x over here, e to the 4x in the denominator. Well, e to the 4x is basically just e to the 2x quantity squared, right? Because you can just, again, you take this 2, you multiply it by 2x, you get e to the 4x. And so it may be helpful to let u equal e to the 2x such that du is equal to 2e to the 2x dx. And now we can go ahead and start working on this. So we have over here an e to the 2x times dx, but we want a 2e to the 2x, so we can just put a 1/2 outside and then write this as 2e to the 2x. And then this is over here 4 plus, we can write this as e to the 2x squared. And then here we have a dx, so now we have dx, 2e to the 2x, e to the 2x quantity squared. That's just going to be equal to, if we substitute, we get 1/2 times the integral of, this is going to be du over 4 plus u squared. And now we're almost there. We have this 4 here, though. That's pretty annoying. But what we can do is we can just factor it out of the denominator. So this is equal to 1/2 times essentially 1 over 4 times 1 plus u squared over 4 du, which is equal to 1/2, or we can bring this 4 out, so this just becomes 1/8, 1 over 8, times the integral of 1 over 1 plus, here we have u squared over 4. U squared over 4 is really just u over 2 quantity squared, right? So u over 2 quantity squared du. But now we just need to do a little bit of work here because we have a u over 2. Instead, we kind of just want one variable on its own to be squared. And so we can do another u substitution, or we can call it like a w substitution if you want. We can let w equal to u over 2, which implies that dw, if we take the derivative with respect to u, is just 1/2 du. And here we have a 1 over 8, which is just 1/4 times 1/2. So this is really equal to 1/4 times 1/2 du over 1 plus u over 2 squared. And we can go ahead and now substitute. 1/2 du is just dw. U over 2 is just w. And so this is ultimately 1 over 4 times the integral of dw over 1 plus w squared. And now we can just go ahead and integrate. 1 plus w squared, 1 over 1 plus w squared rather, is just arctangent of w. This is ultimately 1 over 4 times arctangent of w plus c. And then what we can go ahead and do is we don't really want it in terms of w, and we don't want it in terms of u either, so we have to back substitute twice. So if w is equal to u over 2, what is u in terms of x? We said it's just e to the 2x. This is ultimately e to the 2x over 2 is what w is. So this is just 1 over 4 times arctangent of 1/2 e to the 2x, and then plus c. And that right over there would be your final answer. So essentially, all that we're doing here is we're essentially using u substitution twice in this case, which you can definitely do. You can use it as many times as you want, whatever is preferable for you, in order to ultimately simplify this integral into the form of arctangent of something, or a constant multiple times arctangent of something. And so essentially, really, all that this is that you can use these different arctangent or inverse trig identities in order to ultimately end up with a much more simplified integral when you're doing these very complicated looking rational functions, or when you're integrating these complicated rational functions. And in the next video, we're actually going to apply this notion to arc sine of x as well, the inverse sine of x, which we'll come to find is a little bit more complicated, but still really simplifies the integration process.